Okay, so the lesson's on curl and divergence here. And just as a repeat here, the del operator, also called the nabla operator, is a vector of partial derivatives. It's not really a vector, it's a vector operator. We've seen it before in the gradient of f, which is sort of like a scalar multiplication. You apply the del operator to f, and you're just applying partial derivatives to f, all of the partials. So remember, the gradient is also referred to as the total derivative sometimes, because it just has all the partial derivatives bundled together. And then the del operator can also be applied to vector fields. So we've already seen what a scalar multiplication is with a gradient. But that would only work with a scalar valued function. What if the function is vector valued? Well, there's no scalar product, but there are dot products and cross products. So for this vector field, capital F, there is the curl of F. Okay, which is easiest to write as just del cross F. Okay. And I almost don't like going any further than that, other than if I go further, then it gets ugly, if you know what I mean. So I don't know. I mean, what does that mean? Well, I know with cross products, that I would normally put an ijk in the top row. And then the two vectors in the next two rows. So here the vectors are del, the nabla operator, or the del operator, like, which I would put in the next row, maybe without these commas. Isn't that weird? Like that. And then finally something that it operates on, which is the field itself, and you would just put P, Q, and R down there. Okay, so that's the curl of a vector field. And again, this is not really a cross product, because cross products are full of multiplications, and there aren't any multiplications here. Okay, so, but there are applications of operation or of operators. So I guess, you could pound this out and say that it's I times, see, you would multiply it like this. So it would be R with respect to Y minus Q with respect to Z. So you would say RY minus QZ. Okay. And then minus J. And diagonally like this, you'd have Rx minus PZ. And plus K. And here we'll do this determinant. So it would be QX minus PY. Okay, any questions? Obviously we put that as in bracket notation. So we'd have the RY minus QZ, comma, probably write PZ minus RX, comma, QX minus PY. Okay. Any questions? So that's the curl. Nobody memorizes these. The only formula that people memorize is the first one. That the curl is del cross F. Okay, that's what people know, and that's what you'd be expected to know. And then the question is, do you know what to do with that, right? Okay, any questions about this? It's kind of ugly, right? And what does it do is the next thing. So we'll try and get some meaning out of this, but right now I'm just laying down sort of the computations. There's another computation so much easier because dot products are easier, right? The other vector product is the dot product. So that's called the divergence. So div F is short for divergence of F. Okay. And I'm waiting for that to appear. Hey, I have a question for you guys while we're waiting for this to appear. I'm wiggling my fingers. Do you see that? That is so weird. So it's the screen share that doesn't work, but the regular, how weird. So it's like, to me, this thumbnail is more complicated than these rough notes that we're taking. There's so much less detail in the notes that we're taking than in a video, right? So much less data that's passing back and forward. It's sort of lame. I'm still waiting for my screen to update. And oh, that's something. It's not there yet, you guys. I'm still waiting. Just take a little mini vacation. I'm checking my router status. What I need to do is like get on a web page and see if the rest of the internet's working. So I think I'll do that quick. My favorite website, ebay.com, loads in no time at all. Amazon.com, second favorite website, loads in no time at all. Weather.com or Weather Underground, my favorite weather website, loads in a little bit of time. It's always a little slow. We'll blame on them. Okay, so the internet's fine. It's not a local issue. This appears, yeah, it's fine. So this appears to be a Zoom issue. What do you guys think? Should we crash the meeting and restart it? You think that would be worth it? Are you guys up for that? I mean, it's still not really updating itself. Oh, there it goes. Okay, look, I'm gonna try this, and if this happens again, I'm gonna kill Zoom and I'm gonna restart it. Okay, we're gonna murder it. All right, so we got the div of F, which is short for divergence of the field, F. Okay, I need some space. This is, as you might guess, it's the third of the scalar, of the vector products. So it's the dot product. It's del dot F. Well, that's sort of crazy. So del is up there. And F, of course, is PQR. Like that. So, and also don't forget dot products are scalar products. Okay, so this is just going to be partial with respect to X of p plus partial with respect to x of q plus partial with respect to x of r. And of course, so much simpler, so much easier to compute. Px plus, sorry, that middle one should be, oh, look at that. I did that 3 times. These are partials with respect to y and z. Sorry about that. Of pq and r. So it's px q y plus r z. Sorry about that. Okay, so those are them. Now, it's easier to go into 2 dimensions to do examples to just sort of show what these things tell us. Okay, so first thing I want to do is to I'm going to bring back a couple of vector fields that we've looked at previously. So I'm going to leave this page real quick. And I'm just scanning through for my clever little vector fields that we did. It was 16p, I guess. Pardon me. Here they are. These 2 guys. I'm going to erase a lot of this, so I won't expect you to do this all again. But if you could do quick sketches of the fields and the definitions of the fields, so I'm going to erase anything in here that's green. Well, actually, I like the word swirling rotation. That's good. Okay, those 2 guys. And what I want to do is look at the curl and the divergence of each of those fields. So go ahead and just do quick sketches of those and their definitions here. Nothing fancy, just vectors all pointing to the middle or vectors swirling around the middle. Okay. Okay, so on the first one, this rotational one, let's do the curl of F. So when a field doesn't have a z coordinate, just assume it's 0. So if we do the curl of this field, this is del cross F. Okay. As you know, del has 3 partials in it. F is going to have negative y over 2, x over 2. And then 0 for the 3rd coordinate. Okay. And so then we do the determinant. Pardon me for a sec while I grab that. Okay, so that's how you do a curl. You're going to have a negative y over 2, an x over 2, and a 0. So with the I component, you can see you're going to be doing 0 minus the partial of x over 2 with respect to z, which is also 0. So the I component will be 0. Okay, the j component will take the negative of this sort of determinant this way. Partial of 0 with respect to x is 0. Partial of negative y over 2 with respect to z is also 0. So you're going to have another 0. Okay. And now the third coordinate, the k component, we're going to do this cross product here. So the partial of x over 2 with respect to x is a half. Okay. Minus the partial of negative y over 2 with respect to y, that's negative a half. So that's interesting, it just comes out 0, 0, 1. Okay. That's the curl. We notice that the curl is perpendicular. So the curl basically is an axis of rotation. Okay, this is k, by the way, the k unit vector, right? And that will be true in general. Okay, any questions? So right now we're just talking about the direction of the vector. Later we'll talk about the magnitude of the vector. Remember, every vector has direction and magnitude, and they're both supposed to mean something. Okay. So we're going to have to work a little harder to get the magnitude. But right now I want to do the curl of my vector field F. So let me extend this a little bit. So I don't know how this one will work out. Here we go. Curl of this second vector field, also called F, is del cross F. And it's going to be similar to this one over here on the left. Obviously, I'll be switching things around a little bit. So I'm just cheating a little. Let me zoom in on that so you can see it. Okay, so the components are different though this time. They are negative x over 3 and negative y over 3. Negative y over 3. Okay. And once again, we'll do the determinant real quick. like that. And for the I component, I think we just do this in our head here. So for the I component, we do this. So the partial of 0 with respect to y is 0. The partial of y over, oops, no. Okay, so the partial of y over 3, negative y over 3 with respect to z is also 0. So these partials are both 0. Okay. J component will take the negative of this. Partial of 0 with respect to x is 0. Partial of negative x over 3 with respect to z is 0. So again, it's 0 minus 0. You change the sign, still 0. Okay. Third component. The k component, we go this way. Partial of negative y over 3 with respect to x is 0. Partial of negative x over 3 with respect to y is also 0. So once again, 0 minus 0 is 0. Okay, so the curl is an axis of rotation. This one is irrotational. So I guess the only thing to make of this is that the field is irrotational. And the curl of the field is 0, and that will always be the case. Curl will always be an axis of rotation. If there is no rotation, then you can't have an axis. Any questions about that? Alrighty. We'll keep going then. Let's do the divergence of each field. Much easier. Okay, so div f, remember, is del dot f. Okay, so this should be easy. So the vector of partials, let me grab that. Partial operators comes first. And then dotting with the first field, which has components negative y over 2, positive x over 2, 0. Okay. Any questions? So I guess you're going to have the partial of that with respect to x of negative y over 2 plus partial with respect to y of x over 2 plus partial with respect to z of 0 is 0. Okay? So the divergence is 0. Now, I'll talk about what that means after we do the divergence of the other fields. So I think I'll bum some of this real quick and change it for the next field. but the components are different, so let me fix that. So this field, the new f is negative x over 3, negative y over 3, 0. So the divergence of that field is the partial with respect to x of negative x over 3 plus the partial with respect to y of negative y over 3 plus the partial with respect to z of 0. And of course, this one's going to be negative a third plus negative a third. So the divergence is negative 2/3. Okay, so I think that kind of nails it down pretty well. So for as far as the computations, any questions there? Okay, so let's go, as far as the divergence goes, let's look at this one here. So on this one, I think one point to note, wait, before I go there, is I just want to add convergence and divergence are opposites. Okay, so on this one, the vectors are converging. Okay, so the divergence is negative. Okay. If the vectors are pointing away out from some center, then the divergence would be positive. So when the vectors diverge, divergence is positive. And that just sort of means the vectors aren't parallel. Okay. If you look at vectors, they're sort of coming together. Okay. And it's sort of talking about sort of a compression where everything's kind of pushing to a point. Okay, any questions? Any questions? Okay, so let me zoom back out here. Maybe it's worth, I don't know about this. One of the things I want to get with this field is the vectors are not converging or diverging. They're mostly parallel. Nearby vectors are basically parallel to each other. So there is no convergence or divergence in this field. So the divergence is 0. Okay. Okay, is there any question about any of this? So the divergence tells us whether vectors are sort of compressing together or pushing apart. The curl measures the swirl in a field. Okay, any questions? So let's go down here. And I also should mention on this one, how can I do that? I should also mention that on this one, the curl of the field was K, right? And that K is the axis. Of rotation. And also notice that if your thumb sort of points in the direction of K, it's going to be perpendicular to this plane pointing upward. And you get a sort of a right-hand rule for the direction. So the direction of the rotation is determined by a right-hand rule with your thumb as the curl. So I'm doing a right hand rule with the curl equal to your thumb. Gives the rotational direction. So there's all kinds of info that you get from this, the curl. To me, it's just an absolutely fascinating vector, and I can't say that entirely comfortable with curl because it's, you're taking a cross product of something that's not a vector. So you can't talk about the relationship. Curl, or the cross products always kind of tell you about the relationship of one vector to another and sort of how much space they span out as you go from one to the other. You can't really talk about that with the curl because there's only one vector. But it's still measuring something super duper important. I think we're good here. I guess I could add over to this one here that just as a reminder that curl of this field was 0. That's a 0 vector. Okay. Again, so the field is irrotational. Okay, so you can't talk about right hand rule. There's no curl. Okay, so does anybody, one more chance, any questions about any of this stuff? And would you like me to pause for a moment to catch up? Just say the word or type the word. Everything's fine. Thanks, Chris. You're the best. Okay. I know I teach super slow. At least that's how I feel when I watch because I've been doing all these stupid YouTube videos and I go, oh my God, I'm so slow. Sorry about that. Just a quick primer on divergence. So when you see vectors, well, let me do converging vectors, or sorry, diverging vectors like this. And a lot of this stuff, you see a lot of these mathematical you see divergence and curl in really important areas, like you'll see it in the laws of thermodynamics. You'll see direction and curl in Maxwell's equations, which are the field equations for electric and magnetic fields. So the curl of those fields and divergence of those fields are super important. We'll talk about that in a bit. So here, at this point, the divergence of my field will be greater than 0. Remember, divergence is a scalar, okay? And this is called a source. Okay? It just sort of means that if this was a fluid, that it's sort of just flowing outward from this point. I don't know where it's coming from, but it's like a source, right? It's bubbling up from this point and flowing outward. Okay. And then, of course, the other case which we just looked at was when the vectors are sort of coming together. They are converging. And so in those cases, the divergence is less than 0. And at this point, that's called a sink. And it's like, and I think literally it's like the sink with a drain in it, you know, and the fluid's going down the drain. It's disappearing rather than the opposite, where it's bubbling up the drain, which nobody ever wants to see. It can never be a good thing when your drain is a source and not a sink. Okay. But if the divergence is equal to 0, then you don't have, your vectors kind of have to be parallel so that nothing's compressing or coming apart. So, you know, if I have parallel vectors like this, locally, just locally, I don't mean everywhere, okay? That doesn't look parallel. Just like this. Okay, then here at this point, the divergence of f is equal to 0. Okay, and that's neither a source nor a sink. Okay, any questions about that? Everything fine, Chris? Wait, who was it that said, how's it, and how's it going? Hi, how's it going? How's it going? How's it going? Is it going okay? All right. Hang on, I want to check my notes real quick because there's something I would like to bring in. Here it is. How are we doing for time? 7:04. Let's even get this example in. Okay, so real quick, I want to talk about just kind of a little more detail. We said that the curl is an axis of rotation, but I also want to talk about the magnitude of the curl. Okay, so here's the question. How is curl F related to rotational motion in a vector field? All right, so what I'm going to do is I'm going to create, first of all, I'm just going to draw a bit of a circle here. Oops. Okay, so this is a sort of a path of rotation that we're being forced along. So this is, you can think of it as a force or a fluid flow. That little point right there is my position. And here's my field vector. Okay, so my field's just going to push me around the circle, and you know we could define that vector anywhere, but I'm just going to do it at this one point. Okay, so let's just go ahead and say that that the field causes rotation about the origin. At angular, so it's going to actually be just a velocity. So with angular frequency omega. Okay. So this point right here, its position vector is just going to be x comma y. That's not the field, that's the position. Okay. So first of all, I know that the field, and let's go ahead and call that position vector r for radius, or we always use an r for position vector. So that's position r. Okay, and I know that my field needs to be perpendicular to r. Because I'm moving on a circle. Okay, so if r is a position vector, and of course that means the coordinates are x, y, then the field has to be perpendicular to that. So we know that the field has to be some multiple of, and k could be any value, not zero. Then it has to be some multiple of negative y comma x. Okay, so just note that the field then dotted with r is going to be k, oops, k times negative y x dotted with r, which is xy. And I don't know if you can see that that's zero. So this is k times negative y x plus xy. So that would be zero. So that's all I'm saying is that the field has to be some scalar multiple of negative yx, and the scalar can be negative, and that would cause it to rotate in the other direction. That's fine. Okay, let me put a theta in here. So here's my angle. Right there. And I want the magnitude of my fields, because this is a velocity field. I want the magnitude of my field. Oops. To be the, we'll go ahead and do it this way. F is velocity. Okay, so the magnitude of the field will be speed. Okay, and speed is just sort of by definition r omega. That's the speed as you go around a circle. And I guess I could do r as the magnitude of r. So let's put a magnitude symbol around that r because it's the length of the position vector. So normally angular velocity is r omega, but here we'll do proper math notation like that. And of course, the magnitude of r is the square root of x squared plus y squared, and then times omega, like that. So that's the magnitude of the field. Let me go ahead and do U as the unit direction for F. So this is going to be the unit direction for the field F. We already said we know the direction of the field, so all we have to do here is take this k times negative y comma x and divide by its magnitude, which would be the absolute value of k, times the square root of y squared plus x squared. Okay, so that's the unit vector. That is the direction of the field. And so if you put both of these together, the magnitude and the direction, the field here has to be equal to the speed of the velocity vector times the direction of the field. Okay. So the speed is the square root of x squared plus y squared times omega. Okay. And then the direction is just this k. We'll assume k is positive. So we're going counterclockwise around this. Okay. So this means we can just do k times negative y x over the square root of y squared plus x squared, just to make that a unit. Oh, there's a k down here also. I dropped the absolute value. Y squared plus x squared, dropping the absolute value because k is positive. And so you get a bunch of cancellations. And so the field, a rotational field with angular velocity omega, is just omega times negative yx. Okay, so we may as well just say, all right, well, that's negative y omega x omega. Okay, so that's just a constant velocity, or I should say constant angular velocity rotational field. Okay, and the curl of this field is what I'm interested in. So that's del cross F. So, and I expect it'll only have a k component because the rotation is in the xy plane, and the axis of rotation, therefore, is the z-axis or the k unit vector if you want a unit vector. So anyway, so the curl will have only a z component, something times k. So we'll do this real quick here. Okay, like that. And here we go. So for the I component, those are both 0. So you get a 0. Okay. For the for the j component, partial of 0 with respect to x is 0, partial of negative y omega with respect to z is 0, so it's 0 minus 0, change the sign, you get 0. And for the k component, partial of x omega with respect to x is omega, minus partial of negative y omega with respect to y is negative omega, so there's a double negative in omega, like that. So of course this is 0, 0, 2 omega. So again, this is an axis of rotation. This is parallel to k. You know, I may as well just say that this is 2 omega times k, which is our axis of rotation. Okay, but then the magnitude of the curl, I think it's easy enough just to say the magnitude of curl of f is the magnitude of 2 omega k, which would just be, you know, 2 omega, 2 maybe absolute value of omega. So if omega is positive, then the curl of the field is twice the angular velocity. Of rotation. Okay. So curl F is axis of rotation. Right? Magnitude of curl F is 2 times the angular velocity. So it's sort of a rate of rotation. Okay. Okay, hey everybody. Okay, so we're going to pick it up again. Let me just check and see if anybody's put any messages out there. Okay, so I do not see anybody asking questions. That's fine. I got a couple more things to say about this. Several things actually. Okay, so we're going to continue now. Okay, I want to talk a little bit about Green's theorem. Just real quick, we have to do a couple of two-dimensional things. So, for a field that looks like this. P, Q, both functions of x and y, okay? The curl of the field is del cross F, okay? And of course we've done this already, but I'm gonna do it again. Oops. Okay, so there it is. Just real quick. So the I component is going to be Q. Oh, that last component should be 0. Okay, so the I component is the derivative of 0 with respect to y, which is 0. You have to remember, you know what? It's too bad. But you have to remember that P and Q are both functions of x and y. So I don't know if I can squeeze that in here. But now all of a sudden it sort of becomes important. Yeah. How about that? Okay. And so when I take the I component, I'm getting a 0, but then there's the partial of Q of xy with respect to z. That partial derivative is going to be 0. So it's 0 minus 0. The j component, the same thing is going to happen. You take partial of 0 with respect to x, which is 0, and the partial of p of xy with respect to z, also 0. So you're getting 0 for the first coordinate, 0 for the second coordinate. And the third coordinate, partial of q with respect to x, that's qx, minus partial of p with respect to y, that's py, like that. Okay, so that's the curl of a two-dimensional field. Any questions? Yeah, everything's two-dimensional right now. Okay, Alexa, turn on the bedroom lights. Hey, one more. Okay, and we had a test for conservativeness for two-dimensional fields. So that in 2 dimensions, we said that py, well, let me just go back. Again, I think this was 16.3, right here. Test for conservativeness. Py is qx if the field's conservative. Okay. Okay, but notice if py is equal to qx, just notice that implies curl f will be 0. Now, given our prior discussion, where we've shown that the curl is an axis of rotation and it's also related to the rate of rotation, we can now take this to say that conservative vector fields are irrotational. Okay. And remember, the conservative fields are the ones where when you do work, where you move in a field, the energy that's used to move from one place to another is just the change in potential energy. That's only true in a conservative field, okay? And conservative fields are the ones that don't have any rotational motion in them. Okay, any questions about that? Okay, so that's important. How about in 3 dimensions? In 3D, remember F, let's say, equals PQR, is conservative if there exists, let's see, a scalar valued function. That's the potential function, which is related to potential energy, you may remember, such that the gradient of the little scalar function is equal to the vector field. Okay, so that's what it means if that it's conservative. Now, just to kind of put this all out here, gradient of little f is going to be little fx, little fy, little fz, okay? But this is equal to big F, which is PQR, which is big F. Okay. Now, we want to get that same sort of idea of a test for conservativeness. So, for example, let's look at the mixed partials. So, for example, P y would be which mixed partial? Oh, I'm frozen. Somebody says I'm frozen again. I hate that. And nobody in my house is on the internet right now. There we go. Hang on. It's still coming. The amazing thing is my screen, I've actually showed, oh, there we go. I was gonna say I've shut it all down and my screen's just not updating. There we go. This is what I want. I have to pause now while you guys write what I wrote. Frozen again. Right, so this is just a kind of a reminder of what all these things mean. Conservative fields have potential functions. Potential functions are scalar functions that, or whose gradient is a vector field. Okay, that's just what it means to be conservative. And those are the ones that have conservation of energy, and those are the ones for whom work is computed by just subtracting the potential energies. Okay. And so the gradient of little f, which is the vector fx, fy, fz, should be equal to big F, which is PQR. Okay. Now, the partial, we're doing mixed partials. Which mixed partial is PY? PY would be F. Okay, yep, FXY. Because P is FX, right? PY is FXY. But mixed partials, doesn't matter what order you do them in, so that would be FYX. And FY is Q, so this would be QX. Okay, any questions? So that's what PY is. Okay, now we could do PZ, I think. That would be another mixed partial. So let's do PZ. So PZ would be FXZ. You follow me on that? But of course, the order of mixed partials is irrelevant, so I could call this FZX. So which one is that? That's RX. Correct prescription. So I've got, what other mixed, there's only one mixed partial left. I got FXY, FXZ. What about FYZ? That's the only one missing. So FYZ is the same thing as FZY. So what are those? FYZ, is that QZ? Equals RY? Is that right? QZ is FYZ, which is FZY, which is RY. Yeah. So that's like a 3, and that there's no other mixed partials. Every mixed partial has been brought up now. Okay, so this is sort of a 3D test for conservativeness. Okay, any questions? Now, I have to look back. Forgive me while I go back. Way back. There it is right there. This guy is a curl of F. That I'm wiggling here. So I'm going to copy that. Okay. And just add note that curl F was computed previously here. Now, what's RY minus QZ? Well, the third rule here says those are equal. Okay. This is 0 if conservative. Oh, let me put the if up above. So this is 0 if conservative. Okay. PZ minus RX, that's the second one on here. PZ is equal to RX if it's conservative. So again, that thing is 0 if conservative. Okay. And then finally, PY is equal to QX if it's conservative, and QX minus PY will be 0 if conservative. So this is the 0 vector if it's conservative. Okay, so here's a 3D test for conservativeness. This also works 2D, right? So the field F is conservative when the curl of F is 0. That's a 0 vector. This tells us again that conservative fields in 3D are irrotational. Oops. How you guys doing? I haven't done much in the way of computation. It's been very sort of a theoretical discussion. Apologize about that. So that's the test for conservativeness. Okay, everybody okay? I have to take another step. So just real quick, a quick reminder. I'm gonna jump over real quick to some other notes. Okay, so I want to remind you of Green's theorem. Okay, so this was for a line integral that was on a closed loop. So there's my loop, I'll call it C, with a counterclockwise orientation, and inside here is a region R. Okay. And what Green's theorem said was, now there's a couple of different ways to say this. The simplest is that the line integral around C counterclockwise of f dot dr. So that's just a work integral, but it's also sometimes called a circulation integral because you're just taking the component of the field that points in the direction of displacement. That's what f dot dr does. Multiplies by a bit of arc length and adds it up. That this is equal to, well, if the field is a PQ, okay, and dr, well, let me move this a bit. Okay, if PQ is the field and dr is like a dx dy differential, it's a vector, so it has two components, dx dy. Okay, that's just a restatement of this thing. Okay, but this is also the same thing as if you just take the dot product, and that becomes p dx plus q dy. And I think we did some examples of weird integrals like that. And Green's theorem just says that this can be converted to a double integral over the region inside of qx minus py. And I got some funny spots on my screen where the pencil doesn't work well. Okay, qx minus py dA. Okay, so we're going to try and get some meaning out of this now. Okay, so the first one is actually super easy. I think we did the curl in 2 dimensions. Let me back up here. Here it is. So going back from this statement here, the curl of the field is this thing. Okay, so I'm going to backpedal a little. So my field is just components p and q, both functions of x and y. And we've already determined that the curl of the field ended up being, and it's del cross f. But that ended up being 0, 0. I can't remember if it was, I think it was qx minus py, but I have to double check because my memory's that bad. Qx minus py. All right, which, you're meant to say, oh, that looks familiar. And so I want you to do the following. If we do k and dot this with curl f, well, let me turn it around. So if we do curl f and we dot this with k, then this would be 0, 0, qx minus py. And you're dotting that with 0, 0, 1. So this is just qx minus py. Okay. So, and the only other thing I would do is sometimes we like to make areas and arc lengths vectors. So if we define dA with a vector symbol over it as k times dA, the scalar, just note that curl f dotted with dA, the vector differential, just like dr is sort of a vector differential for arc length. Even though our arc length is a scalar, we have a dr that's sort of a displacement. The length of the vector is arc length. Okay. So curl f dot dA would be curl f dot k dA. Now I'm putting the hat on the k, and we already said this is qx minus py dA. Okay, so I want to make this thing look like down here, double integral of the curl of the field dotted with dA, the vector differential over the region R. And this is what's a very important theorem in calculus. It leads us to this statement. This is a 2-dimensional Stokes theorem. There will be a 3-dimensional version that's almost identical to this. Okay, so the 2-dimensional Stokes theorem just says this. This work integral, f dot dr, counterclockwise around curve C, is the same thing as a double integral over the region contained by C of the curl of the field dot dA. Now, just a couple notes out of this. If the field is conservative, then it's irrotational. So we get information about statements like this, and we want to be able to read a statement like this as intelligently as possible. So what was I saying? If the field is conservative, it's irrotational. So the curl of the field is 0. Can you read that? Curl of the field is 0 for a conservative field. And we know if the field is conservative, then the work around a closed loop is 0. Because there's no change in potential energy. If the curl isn't 0, then the work isn't 0. I might say that. Let me zoom, I'll come up a little higher here. This is difficult because my there's something funny about my glass, so I don't. It's hard to take notes right now. So I'm going to add to this and say if the curl of the field isn't 0, then it is able to do work on objects to move them in around closed loops. Like curve C. I guess I should use easy C. Okay, so we've got this closed loop. We're trying to see if the field can move us around that loop. And only can be done if the field is rotational. There must be a curl for that integral to not be 0. Okay? So that's really important. And a visual representation of what? Oh, of Stokes theorem. Well, I would try and just think the visual representation is just some field pushing an object around in circles. Okay, so if you can visualize that, oh, the curl, element of the curl, but anything is fine. Well, remember, the curl is an axis of it gives information about the rotational nature of a field. So the curl being non-zero means that the field can move things round and round. Okay, it has a rotational element in the field. And all we're saying is that fields like that can do work on objects to move them around closed loops. Does that make sense? Only if the curl is not zero can the field do work to move things around loops. Otherwise, if the curl is zero, then the field isn't doing any work. It will not contribute to the motion. And if you're able to go around in a circle in a conservative space, it's not because the field is helping you. Okay, the field that is conservative cannot make this happen. You have to provide your own kinetic energy, basically, and then you can start, looping around in circles. It's just like you ride in your bike. If you ride around the block on your bike, let's say there's a hill, okay? As you go up the hill, you're doing negative work. The field is doing negative work on you. And then you come back down the hill later on the other side of it, maybe, and now the field is doing work on you, and the negative work and the positive work add up. In the end, you come home and you're in the same place you started, so your potential energy has the potential energy is not changed overall, and so the work that gravity did was zero on you to make you go around that closed loop. Now, you had to do a lot of work, but that's not gravity. We're talking about the conservative field, which is gravity. Okay. Yes, gravity pushed you down the hill, but you had to push yourself up the hill. So gravity did not contribute. Anything it gave you, you had to put it down as a down payment, basically. You have to climb the hill before you get to go down it. And in the end, the gravity's done nothing for you. Because it's irrotational, it cannot make you go around loops like that. Not unless you're going to put, a motor on it or a person on a bike that's pedaling. Okay, you can make it go around circles, but gravity's not going to help you. Now, a rotational field, I've mentioned this before, but the way electric fields work is interesting, where you can have a current going through a wire, okay, like this. So this is an electric wire. And I'm a math teacher, okay, so with current. Okay, and those of you who have studied physics know that when you do that the magnetic field goes around like this, okay, and it loops around the wire. Now that's a rotational field. So, am I frozen again? Oh, damn, this is so annoying. Here we come. There we go. So when charged particles go through a wire all in one direction, it's easier with direct currents. It's just crazy with alternating currents, but although it still works, it's just messier. But with a direct current where the electricity is just going in one direction, then you have an electric field that goes around in circles, and that field can push things around in circles. And so that's sort of that's a very much an oversimplification of how an electric motor works. A field like that is rotational, so it can do work and accomplish things for you. Okay, it can create these circular paths. It can make this motion, but it's not, yeah, gravity is conservative, but a field like this is a magnetic field. Goes around the wire. And so the field is actually, there's lots of vectors like this that are basically forcing motion in a circle around the electric wire. Okay, am I frozen again? Please tell me I'm not. No. Okay. Yeah, so the magnetic field goes around in a circle. It is rotational, so it is able to do work, and we make motors using electric wires and electricity going through them. Okay, and these magnetic fields can push magnets, and when you push magnets around, you make motors. Okay, but no, gravity is conservative. It's non-rotational, and unfortunately, you can't have gravity make a motor for you because it is incapable of moving things around in circles all on its own because it's just not rotational. But electric fields are different, and they're helpful in that way. Of course, you have to supply energy to make the electric current. Nothing's really free, but that's the idea. Okay, any questions? Magnetic field goes around the wire. So it is capable of doing work. To move things in circles. Okay, so there's all kinds of meaning that you get out of this. And I could kind of keep talking and talking because it's just so, you know, what I was thinking about doing is showing you guys Maxwell's equations, which are all about basically how magnetic and electric fields work. And they also kind of, anything that's electromagnetic, which is light, but charged particles, and these electric fields that we're talking about. And so let me see what I've got here. I don't have time. And to be honest with you guys, again, I'm a math teacher. And so let me just share this with you and understand that I only understand this so much. My son was a physics major before he turned into a math major, so he understands this way better than me. So right now I'm just on a Wikipedia page with Maxwell's equations, and I'm just searching for all of the field equations for Maxwell's. There are integral versions and differential versions of all of Maxwell's equations, and what I want to do is just show you the differential versions. Okay, so these are Maxwell's equations, and these are pretty much the equations that govern electric fields. And I don't know a lot about electricity and magnetism, but I know that E stands for an electric field. And you see they do it in bold fonts to tell you that's a vector field, okay? And B is magnetic, okay? So I can read a few things from this. This del dot E, that's the divergence of the field. And they're saying that the divergence is not zero for an electric field, okay? And in fact, electric fields point in toward a charged particle. So if you've got just like an electron, okay, it's a charged particle, and the field point for an electron, I guess it points in. The field points into the electron, and forgive me if I'm wrong about that. It's either in or out, but I think it's in for the electron. So you've got these electric field lines that point, or vectors that point in to the charged particle, or out, depending on the type of particle. And so the divergence is not zero, which means the vectors are either coming together or pushing outward. okay? So that's the nature of an electric field. The divergence is not zero. Remember, divergence is del dot E. Okay? It's not zero, which means they are sources and sinks where vectors come together or push apart. I learned also about the magnetic field. The magnetic field, the divergence is zero, which says that magnetic fields are incompressible, like fluids. They can't be pushed together, and they can't, the way the vectors point toward a charged particle in an electric field, you don't get that in magnetic fields. In magnetic fields, the vectors, if you look at them really close together, they're always sort of parallel, okay? So that's something that I know. And I don't know anything about physics, but I can read this and know what this is saying. Okay, look at del cross E. That's an electric field, and they're taking the curl of it here. Okay, now, what they're saying is that the curl of an electric field is not zero, first of all, and it's related to B, which is a magnetic field. So the electric field and the magnetic field are related in some way that I don't really understand. I do know that B is the electric field, and they're measuring how it's changing over time here. See, it's a derivative with respect to time. And all I can tell you is that this curling, right, it's a non-zero curl. So this is a rotational field for the electric field. And remember how I was talking about how you can, oh dang, now I'm confused a little bit. Well, bottom line is electric fields can curl. And so can a magnetic field here. It has a curl as well. So, and I know with a magnetic field that if you run an electric charge through a wire, then the curl is non-zero there. And I see whatever this is relating to the change in the electric field, that I can make a magnetic field that curls as well. Okay, so again, I'm not an expert on Maxwell's equations, but just knowing what these fields are and what these operators represent is important for you, okay? It's not, you guys are gonna be studying this stuff, and you need to be able to look at this and go, okay, so this one's compressible, but this one's not, you know what I mean? And this one's a curling field, and so on and so forth. So there's geometry behind this, and to understand Maxwell's equations and also stuff in thermodynamics, you have to understand the geometry that's defined in these mathematical operations and what the curl and the divergence measure. And you can see all of Maxwell's equations involve either a curl or a divergence. And I don't even like looking at the integral versions of those same equations. I don't even want to think about that. That's a different matter. But although I have to say, before the semester is over, you're going to know what this is. That's a surface integral. Okay, and I think they're computing the flux. You'll know what all this is. This is the flux of an electric field through a surface. This is the flux of a magnetic field through, and by the way, this circle here means it's a closed surface. Okay, we'll be computing that next week. This is the flux of a magnetic field through a closed surface. Apparently magnetic fields do not have a net flux as they flow through a surface. So any place where a magnetic field that flows through a closed surface, where the field has a positive flux, somewhere else the negative flux will cancel that out. The net flux is always zero of a magnetic field through a surface. I don't know anything about this, but just because I understand what flux is, and over here what divergence and curl are, I'm able to make a lot of sense about the nature of these fields and how they interact. So, and by the way, this statement right here is a three-dimensional version of the divergence theorem, which I was going to talk about next. I'm going to see if I can show you the divergence theorem real quick. So I'm going to go back to my notes real quick here. I just had one more thing to say before we're done. I hope I can squeeze it in. I have no promises. You know, like I say, it's my job to make sure you understand what these things are in a sort of a theoretical context. I promise you this stuff is all so important in physics. Okay, so I had to talk a little bit about flux. So I don't know if I'm going to be able to squeeze this in 15 minutes. Let's see if I can do this. Okay, I was looking for that original curve. Let me do this just somewhere else. Okay, so this is again my closed curve C, and my region enclosed is R. I want to go ahead and do it like a dr differential real quick. So remember, R is position, dr is displacement. So I'm going to do like a dr going this way. It's just a tangent vector. I'll probably move it a bit just to make it look like a real tangent. Okay, so that thing is just a tangent differential dr, and if you need to be reminded, dr is r prime of t dt, but it's also just dx comma dy. Okay, and that's the one I want. So I'm going to get rid of the r prime of t dt, forgive me, but there's lots of ways of representing these things. Okay, so that's dr. It's a differential of displacement. Now I want to break this down into a vertical and a horizontal component. Those will be dx and dy. So this is going to take a little time to draw a nice little triangle here. Like that. Okay, so maybe right inside here I'll put a little dy. And down here is dx. Okay. Oh, my bad. Okay, and then what I want to do is make a vector that's perpendicular to this. So how am I going to do this? What I want to do is rotate these. So let me think for a second here. I'm going to try and get these to be the same size when I rotate them. So I'm going to copy this, put it down here. Okay, and now I'm going to do something so crazy you're not going to believe it. First of all, I'm going to erase these, and I'm going to make a circle as a measuring device. That's the crazy part. Okay, so this is my tool for making sure I do this the right length. Okay, I'm going to move that for a sec out of the way. Okay, so I want to rotate this 90 degrees. I'm trying to construct something perpendicular and preserve the length like that. Close enough. Okay, so I'm going to erase that. I still have my dy and my dx. My dx and dy are going to construct a vector that's perpendicular to the first. I know that to make a perpendicular vector, I basically have to switch the rise and the run. Okay, so let me see here. I'm going to do my run first and put it here. Okay, and then this guy here, like that. That's a new vector. Hang on. Going like this. and this is perpendicular. This one's going to be called ds. But it's not an arc length. It's not the arc length. It's going to have a vector barb over it. Okay, now I got to label these quantities because I kept their lengths on the left. I think my dy is negative. This is still negative here, so that's okay. I can keep the sign. On the right, my dx is positive because it goes to the right, but on the left, I want it to be negative. So this is going to be a negative dx here. Like that. Okay, so ds turns out is the x component is dy, and the y component is negative dx. Okay. And just as a reminder to you, when we do work, hang on, I gotta fix that. How are we doing for time? Plenty of time. Okay, so when we do work, it's just f.dr. Field, that's a differential for work. It's not all the work. You have to integrate that, right? How's the screen? Looking good? Okay. What this is it's the component of f that points in the dr direction. Times the length of dr, which is called ds, by the way. So ds, the scalar, is the length of dr, you may remember. If I do f dot ds, this is just like f dot dr, but it's the component of f that points in the ds direction. And that's perpendicular to the curve. Okay, and then that's times the magnitude of ds, which is the magnitude of dr, which is the scalar ds. Okay? So f dot ds, f dot dr is work. F dot dx, that's called flux. Okay. It's the flow of f across the curve C. Okay, and we'll talk more about flux, just like we've spent a lot of time talking about curl. We'll have to get flux straight in our head as we get there. Let me see, where am I? I probably should put a quick reminder of Green's theorem up. It said that the integral of p dx plus q dy is a double integral of, I think it's qx minus py, double checking. Where is it? Qx minus py. dA. Okay, this first one's over the curve C, closed loop. R is the region contained inside for Green's theorem. Okay, so flux is basically the flow of, if you were thinking of this as a fluid flow now, of the field F across the surface S, okay? And so we have to take the component of F that's perpendicular to the curve. Oh, I'm sorry, it says across S. I meant across C, you guys. I'm so sorry. Later it'll be S, a surface. Right now it's just a curve. Okay, and so we would do the flux differential F dot ds like that, and then add this up along the whole curve to see how much fluid is flowing over across this curve. Okay. Think of the curve as just some boundary that the fluid is flowing over. Okay. But then I want to back up and say, okay, wait a minute. So this is F is still this PQ field, but ds was dy negative dx. Okay. And if I just carry out that dot product, I get p dy minus q dx, which I want to write as negative p dx Did I get this screwed up? I'm sorry. It's negative q dx. Plus p dy. Okay, that's just doing the dot product and changing the order, which is fine. Now I'd like to apply Green's theorem up here. Things are a little screwy. I have to change the sign of the second one. Nope, I have to change the sign of the first one, take its partial and put its second. Partial with respect to y. So with Green's theorem, take the first one, take the partial with respect to y, change the sign, so I would do a double negative with a qy here. And then the second one is the q. I take the partial with respect to x and put it first. So here, the p, I take the partial with respect to x and put it first. So I would have a px here. Okay, and then I get the dA. Okay, so what this becomes is double integral over r of px plus qy. Yeah, this is the divergence of the field. So it's the double integral of the divergence of the field, dA. Remember, divergence is a scalar, so there's no dot products there. Okay, so just as a reminder, div f is del dot f, which is, well, del is partial with respect to x, partial with respect to y, dotted with a field which is a PQ. And so this is PX plus QY, which is what we saw here. Okay, so this is a two-dimensional version of the divergence theorem. Okay, and it just says that the flux of the field F across the curve, closed curve C, that's this integral. Oops, that should be a C down there. Field dotted with ds, the vector, like that. Okay. Is equal to a double integral of the divergence of the field dA over the region inside. Now remember, divergence measures whether a field is a sink or a source. So like if you think of it as a source, then water would be bubbling up out of like a drain, like it's like a drain in reverse, right? So we see water sort of coming out of a drain, and the fluid would be flowing outward. And if the edge of the sink is like the boundary, then once the sink starts to overflow, then you've got fluid flowing across this boundary curve, and that's going to have a total flux that's positive because it's an outward flow. That can only happen when the divergence is positive. So if the divergence is positive here, that's an outward flow that will cause flux across the surface. Across the curve, which is the boundary. Okay, I gotta let you guys go, but this gets us a lot of traction in terms of covering material that's coming up. And by the way, when you look at some of those Maxwell's equations and also some of the laws of thermodynamics, they are just restatements of the Stokes theorem, which was above somewhere right here. Stokes theorem or the divergence theorem, these laws generally will just boil down to those. All right, I'll see you guys and have a great weekend. We will not meet again until next Wednesday. Take care, everybody.